Today I'm very glad to introduce you Professor Prem of the University of California at Davis. He authored more than 130 papers. I have to read actually 6 Best Paper Awards, and out of which 4 ACM distinguished papers. These are mainly in ICSID, right? And then he also was in program committee of many of our best conferences like ICSI and EC, and he also editorial board of TSE and TOZL. Yeah. So I'm glad to introduce you, Prem, Exploiting Nature.
Thank you. So it's really nice to be here. Thank you very much for the invitation. So Italy, for me, is kind of the home of academia and academic research, because the first conference I ever attended my whole life was ECAI, European Conference in AI, in 1984, and that was in Pisa. And at the time, you know, AI was mostly about logic and knowledge representation, and I was very excited about that. I was working in that area, and back then there were some really impressive Italian researchers who worked in the area. There's Maria Sini and Giuseppe Attardi. I don't know if they're still in Pisa. In those days they were famous. So, you know, of course, since then my areas of interest have shifted. It's kind of gone back more towards AI, but of course now AI is very probabilistic. There'll actually be a little bit of probability theory in this talk. AI has become much more probabilistic, and you know, mostly a software engineering researcher. And of course, as you know, Italy is one of the most famous and active countries in software engineering. Despite sort of relatively small population size in Italy, it's very well known. A lot of very famous and active researchers in Italy in this field. So it's a great privilege to be invited to give a talk here. Thank you very much. So as I said, you know, I've been in research since 1984. So to echo on Rocco's talk, I have to say, I feel privileged to still be relevant and you know, still be able to give very interesting talks, hopefully that you'll find interesting. Just a little bit about where I'm from. So Davis is one of the 11 University of California campuses. It's right smack in the center of the city. It's a very agricultural area. It's you know, wine, tomatoes, almonds, walnuts all grow there, surrounded by fields. So there's San Francisco, and it's about 80 miles away, Napa Valley, where you can have wine tours, Lake Tahoe, Yosemite. So it's right in the middle of all kinds of great stuff. So if you want to come visit, please do. You know, it's a really fun place to visit, and you can hang out in our lab and see what it's like. All right, okay, so Davis campus is very kind of rural and pretty. One thing unusual about our campus is that it's very bicycle-centric, so there's bicycles everywhere. Unfortunately, in the beginning of the year, also a lot of bicycle accidents, because freshmen who come in the US, bicycling is not very common, so a lot of people come and they're sort of learning how to bike. People fall, and it's a mess, but it's a nice place. Okay, so I have to say, so my first paper was published in 1986, so I've been in this business for a long time. What I'm going to talk to you about today is what I'm kind of, I guess, for my whole career, this is what I'm most excited about working on. I think it's a really neat and fun stuff to work on. So basically, it starts with the observation that human speech and human writing evolved over thousands of years to serve natural human purposes, right? We'll see about what that is in a second. And the argument, this line of work that we've been doing, is that programs are actually the same. So a program might seem in some ways artificial, but they're actually also natural in the sense that they have the same kinds of properties that natural speech and natural writing have. So, you know, so I'm very excited about this line of work. So it first came out in ICSI 2012, and this more recently there's an article in the Communications of the ECM in May, essentially the same article, the 2012 article, has been reprinted. And just to let you know how excited I am about this work, I mean, so in the US, I would say that the least trusted profession in the US is the lawyers, right? right? So the joke they make in the US is, how do you know when a lawyer is not telling the truth? You know it because his lips are moving. Right? So I would say for the most part, you shouldn't trust American male academics, particularly male academics. You shouldn't trust us. You always say what we're doing is great. So just to give you this, this is the introduction to our paper from the CSEM, and this is what I'm just going to expand that portion. Now, this was said by a Canadian woman, a very famous Canadian researcher, Gail Murphy. So I'll let you read that. So this is what she said about this area. She said that this is really going to change the field. It's kind of really exciting new stuff that gives you a completely different perspective on what software is and how software should be studied and how we should build software tools. So you know, it's a really exciting area, and I hope to communicate some of that to you in the talk, and if I fail, it's really my fault. So if you don't feel excited after my talk, please go and look at the paper. It's, maybe that'll be better. I'll try to do that. Okay, so to just give you a sense of what I mean by naturalness and where that term naturalness comes about. So here's a guy who's about to have a very bad day. So, you know, what is he going to do? What is he going to say? He's got the language skills, so he's going to communicate something. Right? So what is he going to say? So it's not likely that he's going to quote from William Blake, "Tiger, tiger, burning bright in the forest of the night." He's not going to stand there and declaim, you know, beautiful verse about the awesome beauty of the tiger. He's going to say, "Run," right? So the point of this is that, you know, why is it that we communicate? It's actually a question I'd like you to think about, hopefully answer. Why is it that people communicate in very predictable, simple ways? I mean, you could have almost known he was going to say that, right? I mean, that's what most people would say in that situation. You knew he was going to say that. He wasn't going to speak that word. So why is that? What is really the essence of language? How did language evolve? What is language for?
Send comments.
Yes, and we want to communicate information. We want to tell our children, run from danger, right? If we see an attractive mate, we want to communicate with them. If we see food, we say, there's food, we want to eat. It's for eating, it's for procreating, it's for surviving. You know, that's what language is for. So it serves a very essential animalistic human purpose. So, you know, people are not going to use language most of the time. You know, sometimes we get very eloquent, but most of the time we use it in very simple, very predictable, very repetitive, very kind of normal ways that, you know, there's nothing surprising about the way we use language. So why is it that we express ourselves simply like tiger run and not tiger, tiger burning bright? Why is that?
It's the fastest way to shop.
It's fastest. We're trying to communicate in a noisy, dangerous environment where time is of the essence, right? I mean, in the African savannah where language evolved, people were trying to tell each other, you know, there's food, you know, there's shelter, there's a mate, there's danger, you know, that's what people were dealing with, you know, hundreds of thousands of years ago. And language evolved under those circumstances. So, you know, so we don't want to be complicated. We want to make sure that whatever we say is clearly understood immediately. That's what the core of it is. So that's why we try to communicate in very unsurprising ways. We're going to come back to surprising in a few minutes, right? Surprising actually has a very clear mathematical notion. It's called entropy. We're going to come back to that in a minute. But so that's sort of the core of language. Now, let's move from the African savannah to Redmond, where a lot of programming gets done, or Bangalore, where a lot of programming gets done, or Shanghai, or Sunnyvale, California. These are places where a lot of programming gets done. And in fact, there are tigers there too, right? Right? And so, how do people respond to this pressure, right? So, when you are under pressure to write code, and the point is not really the beauty and the elegance of the code, that's not the point. Okay, so if you're a functional programmer and you're writing in Haskell, right? Or you're writing an ML or you're trying to show some beautiful application of C++ templates. Okay, so then you're trying to write poetry in code. You're trying to communicate some beautiful idea about how you can generate code using templates or do some amazing thing using monads and functors and arrows in Haskell. Well, God bless you, but most of the time you're not doing that. Most of the time you're trying to satisfy some customer as quickly as possible. And they want their bugs fixed yesterday. They want the new features the day before. They're like the tiger, right? They're not very interested in beauty of construction. So it turns out when they write code, that's the same thing, right? We're writing code under pressure to get things done quickly. So what that means is that the same kind of repetitiveness, unsurprisingness, which can be mathematically modeled in a sense that I'm going to talk about soon, applies to code as well. Okay, right. So this is, oddly enough, this is not that surprising. This has been, in fact, something that has been said before. I'll let you read that. It's like basically saying, don't think about programs as something that tells the computer what to do. Think of programs as a deliberate act of communication from one human being to another, right? And any of you who worked in software maintenance knows that that this is the right way to think about code. Really, code is really read a lot, and that's really the most important thing about code is that it can be easily understood. Okay, there are some situations in which you don't want to write a equals b equals 0. You declare 3 integers a, b, c, and then you do some complicated Boolean transformation to set them all to 0. But you should never do that. I mean, in practice, most of the time, there's no reason to be super concerned about low-level, machine-level optimization or something like that. You want to write code as easily readable as possible because people are going to read it. So this was said a long time ago. This was actually said by Don Knuth. So when he wrote this book on literate programming, the article on literate programming, this was something he said, that programming really should be viewed properly as an act of communication. All right, okay, so where are we? Okay. So where is all this going? All right, so languages, human languages, the point I was trying to make earlier, is that, in fact, they're very rich, powerful, and expressive, right? Their vocabularies are extensive. There's rich use of metaphor, of idioms, of poetic language, of rhyme, meter, all these things. So you can say amazing things in these languages. And and of course there are people who do these things. Shakespeare, I do, Schiller. These are people who are capable of using language in unusual, surprising, beautiful, elegant ways that delight us. And this is certainly there. But most of the time, the way language gets used is simple, repetitive, and boring. Hopefully not like it's talk, but so this is the reality. So why does this matter? Why does this matter? Well, it turns out this aspect of language is now a multi-billion-dollar economic phenomenon. Right? Because languages is property, there are huge fortunes being made. There's a lot of fantastic science and engineering that is being done. All right, and why is that? It's because what we can do is we can capture this property in mathematical models, statistical models, right? And you've probably used some of these. You think many of you may have used LDA. That's an example of a statistical model that is used to extract certain features from language, which exploits this property that language is actually repetitive. And these statistical models are at the heart of algorithms in things like Google Translate and Siri. So why is that? Well, we'll see more as we go along, but roughly speaking, a lot of problems that we deal with in natural language processing, whether it's speech recognition or translation or any of these things, they're actually search problems. So most of the time, they're actually searching through a set of possible interpretations of a speech act. So, here I am. I have a sort of funny mixed American-Indian accent, and probably I'm not a native English speaker. I'm sure quite a few are native English speakers, quite a few are not. But you can understand me, right? So essentially, mentally, you're going through some kind of search process to disambiguate the funny ways I say words, and you can disambiguate them in your head, right? So this kind of search process is made faster and facile in your mind because of the model you have of language. You have a statistical model of language in your brain that tells you what is likely and what is not. And you're very quickly conducting a search through your mind to interpret words that I may not say the way you expect me to say it, but it's close enough and you can sort of say, okay, if he said this, then he must mean that. So essentially you're doing some kind of search in a conditional distribution in your mind of what is this fellow is really trying to say, conditional upon what I'm hearing. I'm hearing this funny sounding stuff, but maybe this is what he meant to say. So because of this ability to model language in these very good, and we'll talk about what good distributions are in a minute, these very good distributions, you're able to sort of disambiguate it. And it's the same way that Siri works. It's the same way that translation works, right? So translation also works in it. Actually, we'll see that in later on. It also works in a similar kind of what's called noisy channel model, which captures how one language gets transformed into another language. So if you have a good model of it, you can sort of recover it, again using some kind of search algorithm. So these statistical models, these very peaky distributions where most of the action is in a small region of the probability distribution, and most of the distribution is empty, this very peaky distribution allows these search algorithms to be very efficient because you can safely ignore a lot of the search space conditionally because nobody's ever going to go there because most people don't speak that way, right? Most people don't talk like Shakespeare or Schiller, right? Don't. They talk in very predictable ways. So, so this is what it's about, right? So the thesis of this line of research is really the same. So programming languages, more and more these days are extremely expressive, right? They have a lot of things you can say in them, right? But most code is simple, repetitive, and boring, right? So one thing I'd refer you to is there's a paper, I think it was FSC 2010 or 11 or something like that, where some people looked at the use of Java genetics. So Java genetics was introduced with great fanfare. This fantastic template feature in Java, and it's going to allow all sorts of things. It turns out the vast majority of uses of Java genetics is in the built-in data structures. Right? Most people when they write code never use genetics. They just use the built-in trees and lists and all this. Nobody ever bothers to write genetics. So for example, I love Haskell, and I teach Haskell in my classes. That's the only time I use Haskell because it's good to teach. It doesn't really have any practical. I never write Haskell for my own programming. Most of my programming is R anyway. So anyway, this is the idea, right? So we capture this property of programs, real programs, and statistical models, and then we can, make development tools much more powerful. So anything in a development environment, anything kind of tool environments, software tool environment, where you can think of it as some kind of search problem, you can make it much faster using statistical distributions. The whole game is to try to find the right kind of statistical models. Okay, so this talk is a little bit strange. More than half the talk is actually science. It's not really engineering. It's more about the science of software and what software actually looks like. So it's a little bit different from the other tutorials, and it's a delicate choice on my part, and hopefully you'll find it interesting. It's a lot of actual phenomena. It's not actually engineering. In the second part of the talk, there's more of the engineering side, and then before we get into that, we'll have a lot of this kind of scientific stuff. All right. Okay. So the first bit of science. So this is by a couple of people from UC Davis, Jay Dogso and Mark Abel. So they're both programming languages researchers that, occasionally from time to time do publish in conferences. And so one of their efforts in the FSC was, this is from FSC 2010. This is a paper that they wrote called The Study of the Uniqueness of Source Code. So I highly recommend it. This is really a kind of very complex experimental job. Required a lot of major bits of engineering. So it's 6 years ago, so the computational power that's available wasn't as good as it is now. So it was very serious engineering in this. And it's a very massive study. At the time, it was the largest study I knew of source code. It was hundreds of millions of lines of source code that they studied. So the motivation for the study was the paper that came out, series papers that came out 2008 to 2009 from this group in Virginia, Wes Weimer's group, where they were doing automatic patching. So this is the work, the genetic programming work that Max was talking about yesterday. So what they were saying was you could take pieces of code from one portion of the program and patch them into another portion of the program to fix bugs. Right? So if you have a program and you have something that doesn't seem right, well, you know, chances are you're going to find something else somewhere else in the code where you can pull it up and fit it in here, and then you're going to pass your test cases, right? And you just keep trying various pieces of code from various places, and you know you can make this work. So when so this is 8 years ago when they saw this paper, they said, well, wait a minute. The only way this could possibly be true is if code that people write is really not unique. That is, code that keeps getting repeated. Right? That is, the same code gets written over and over again. So is that really true? Is it really true that code is actually repeatable, right? That it repeats a lot? Because if it didn't repeat, then we couldn't do this sort of automatic patching by moving code from one place and sticking it to another place. We must have a lot of repetition in code. So, even back then, we had access to huge volumes of code, hundreds of millions of lines of code. So they said, well, okay, why don't we go through this and see what it actually looks like? So that's the motivation of this paper, right? So these are slides from them. So you've heard this infinite monkey theorem, which basically says that if you have enough monkeys and enough typewriters, these are very modern, high-tech monkeys that don't use typewriters. They use, I don't know, have you guys seen a typewriter? Some of you probably have seen typewriters. Okay, so the infinite monkey theorem is that if you give enough monkeys enough typewriters, eventually they'll produce the complete works of Shakespeare. So that's the infinite monkey theorem. And so, the idea is that, of this line of work with programs is that this logic doesn't really apply to programs. Right? Somehow programs are not as varied as human language expression. It's much less varied than natural English language expression. So remember, this is before we did our statistical modeling work. So this was kind of very early work. So they thought it must be different. So in particular, that maybe they thought there's something like a finite programmer's theorem, right? And this is why we can do automatic program patching, because programs are really much less varied than English. We'll see more about all this in a minute, but this was sort of their thinking that that programmers are actually finite. That mental resources of programming is finite. People don't write that many different kinds of code. So the variation that we see in program is less than what we would see in natural language. So these are slides directly from 2010. Right? So I'm just wanted to give the historical background of where the science developed in this. Right? So the idea was, they were saying, okay, look, people are very creative and prolific, and and do all sorts of crazy stuff. And we go to the moon, we write Shakespeare, we compose music, we write the Inferno, all kinds of great stuff. But programming is actually much more conformant. That is, this is a picture of a typical development in California, where I live in, where there's hundreds of houses that look exactly the same. And it's the reason why all these houses look the same is because what they'll do is they'll have the same foundation for 100 houses. They'll bring in people who build foundations. They'll build 100 foundations. And they'll go away, and the next person will come along, they'll put in the walls, and then put in 100 walls. And then they'll bring in the roofers, they'll put the roof in, and so this way they can build houses very fast. I don't know if they do it that way here in Italy or not, but so they can put up hundreds of houses in a matter of weeks, right? And, So maybe programming is the same. So maybe we write programs exactly the same way. We don't want to spend a lot of time and resources writing programs creatively. We want to build them quickly and repetitively. So this was their thinking in how this might actually play out. All right, so they said, let's try and see how much of a program, a particular segment of a program, let's focus on, 6 tokens, 20 tokens, 100 tokens, 70 tokens. Let's focus on this instead. How much of this can we reconstruct by taking pieces from somewhere else? Right? So let's see how many of this can we reconstruct by assembling pieces from somewhere else. So if you take any one token in the program, any single token in the program, it's not going to be unique, right? Any single token in the program probably occurs somewhere else, most of the time, right? Why would you have a token that occurs only once? Even if it's a variable name. You know, if you're not going to use it more than once, why even have a variable name, right? So any single token is going to be repeated, right? So let's take longer and longer tokens, sequences of tokens, and see how often they're actually really unique. Right? So that's what they wanted to study. Okay, so they, you know, for example, they might start with a fragment of code from Linux, something like that, right? And then you tokenize it. You get those tokens. And what you can do is you can take various sort of subsequences of tokens, like maybe 3 token sequences or 4 token, 6 token sequences, whatever. And you can see for each of these groups how often, for example, this particular sequence of 3 tokens can be found somewhere else in hundreds of millions of lines of code. Okay? How often is that going to happen? So that's what they're interested in looking at. All right, so you know, they amassed a huge volume of source code, right? And they basically tokenized all of it, right? And then they started looking to see how often the tokens that they saw in one place would actually be found in a different place, right? So how often would that token sequence be repeated somewhere else? Okay. And once they did this, they made a count of this, right? So this was massive effort, right? So they did this under various circumstances. We'll talk about more than in a minute. So this is a huge, enormous computational effort, comparing all these things. And at the end of the day, they have graphs. Right? So the whole punchline of the paper is a bunch of graphs, right? And you know, I hope you find those graphs as exciting as I do. So we'll get those really cool graphs. All right, okay. So so the question is, when you study this, you have to study it at different levels of granularity. Right? So as I said, a one token sequence is almost all of it is going to be non-unique. Every single token, 100% of the single tokens will be occurring somewhere else. Every pair of tokens, maybe. You know, maybe every pair of tokens also is repeated. Every 3 tokens, less likely. Sequences of 70 or 80 tokens, more likely to be unique, that you're never going to see them more than once. So they studied various granularities. 6 tokens is roughly 1 line, and then maybe 720 tokens, probably a method, a whole method. And then a few things in between, maybe if statements, while statements, that sort of stuff, right? Things, a few levels of that. So they studied all this. And they were essentially looking to see how often those things were repeated. Now, when you think about repetitions, if you look at those 2 loops on the right-hand side, the first for loop and the second for loop, they're really the same. Right? I mean, the only thing that's different is that they changed the variable. There's no reason to consider it unique. Right? So they also wanted to do that. They also wanted to consider variables renamable and find identical code fragments up to variable renaming. Okay, so that's something else we're interested in. All this, of course, really algorithmically complicates the effort required to get all this data. But you know, they were up to it. They were going to do this. All right. Okay. So so they were, you know, basically matching code from one fragment to the next at very large scale across multiple projects. And they're trying to find out which segments were unique, the black bits, and which segments could be matched against other bits. And they did it across multiple projects. They came up with a lot of very serious algorithm engineering to make this go efficiently. And they were interested to calculate the percentage redundancy. Okay, so you can see the scale here: 6,000 C, C++, and Java projects. Now it's interesting that they chose different languages, right? because you sort of have to wonder, you know, are languages the same with respect to uniqueness and repetitiveness? Right? So, what would you think would be more repetitive? Assembly language or Haskell? What is the purpose of high-level languages? What's the purpose of abstraction languages? Say it again?
Oh, so vector understanding communication, right? So the assembly is not really readable for everyone.
It's not very readable, right? So, and also it's kind of very verbose, right? So when you introduce abstraction features into language, like methods and classes and inheritance and templates, what are you trying to do? What's the purpose of it? Say it again? Reduce code, right? So how does introducing a function reduce code?
And we can reuse it.
That's right, you can reuse it so you don't have to repeat the code. So higher level languages should be less repetitive, right? So when we go from C to C++ to Java, what should we see? More repetition, less repetition?
It's more.
Say it again? You should see less repetition, right? So when you go to higher level languages, right? So it's good that they combine multiple languages because it's an interesting question how this all works out. And you know, you can also say that the more repetition a language has, as a programmer, I would find it more annoying, right? So, you know, one thing I find annoying in Java, for example, is why do I have to say throw new? After throw, you always say new. I mean, like, come on, what is this? You know, it's right? And you know, all these import statements in the beginning and all this in Java, you know, so every language has the sort of bits that are irritating, right? So one thing I would love to do, I think it's a great idea, is try to figure out a mathematical way of characterizing irritation, right? There must be a way to do this. I haven't figured out how, but it would be nice to know some way of characterizing how irritating a language is. But anyway, so they studied these 3 languages, and they looked at you know, different types of abstraction. Either no abstraction, that is 2 code fragments are identical if they use exactly the same tokens. And then they also consider 2 code fragments to the same up to alpha renaming. That is, the variables are renamed consistently. Then you consider 2 code fragments to the same. The other thing which is even more complicated is they allowed edits. The reason why they were interested to allow edits, that is matching up to a few edits, is because of genetic programming. That is this automatic program matching. They allow a certain number of mutations to patch, right? So they wanted to see how much this goes on when you're comparing 2 tokens. So they considered various granularities from 6 to 120 tokens. Okay. All right. So this, you know, at the time there was 4 months of CPU time. You know, nowadays we have a $5,000 machine that has 32 GPUs, 128 gigs of memory, and two NVIDIA. Two NVIDIA Tesla cards, K40 cards, so we probably do this in a day. But yeah, so those days it was some serious crunching. Okay, all right. So this is the first plot. I hope you find this plot super exciting. Only nerds find plots exciting, but we're all nerds.